Okay, it gives me pleasure to present Kundan Kumar from Bergen, who's going to talk to us about iterative methods for geomechanics and flow in porous media.
First of all, thanks a lot for inviting me. It has been a wonderful stay so far, and I'm looking forward to the rest of this stay. It's a beautiful place. This is first time to UK, and I'm enjoying it as much as I could have thought, or more or less more than that. So this is on the coupling of geomechanics and flow in a porous media, and it's a joint work with three groups. One is the Bergen, where I am presently located with Jan on bottom and Florin. Raju, Jan was here for some time. And I was doing my postdoc before with Mary Wheeler. And Tamim is a PhD student at Austin. And Vivek Giro is a frequent visitor to Austin. So then this work, part of the work was when she was visiting. So different work has been done with different people. So the applications are the fact that the flow and the mechanics, they have been becoming quite coupled, and it has been realized recently with more and more that you have to take into account the mechanical effects because they can have enormous economic consequences. So for example, because of the gas extraction, you can lead to the loss of fluid from the earth, from this region, for example, and then you can have subsidence type activities. But this is not only because of natural gas extraction, you can have it due to the same thing, due to mining or some chemical influences, and they can all have quite some drastic consequences. So the petroleum industry is quite worried about this kind of troubles that they have to face. I think recently BP had to pay quite some money to deal with their mechanical failures in one of the Mexican coasts, I guess. So now so one of the easy models to describe this, the easiest one in fact, is the single phase flow BO model. And this BO model has the following structure. First of all, it has two parts. One is the linear momentum, which is minus divergence of some sigma is F, which is this stress. And the second part is the flow part, where we have the mass balance. So this is the Darcy part, where you have the flux is equal to minus k grad P, which is something that is very much familiar to everyone, I guess. And this is the mass balance part, where you have the divergence of the flux plus some more terms that are coming because of the compressibility effect. So this is the mass balance plus the linear momentum balance. The point is that the sigma pore, because of the porous medium, this stress consists of two components. One is the usual mechanical stress that we know, and the second is the modification because of the pore pressure of the fluid. So this is the modification that comes up due to the fluid pressure in the porous medium. So this has two components. One is this usual mechanical stress tensor that you know, and with some pressure term that comes from the fluid. So this is the flow mechanics coupling. So if you see here the alpha divergence of U, this is the mechanical term, which comes which is U is the displacement. So this is the change in the, let us say, some kind of a volume. So this basically gives you the change in the porosity because of the mechanical changes that are happening. So this is where this mechanical term comes up in the flow equation. And this pressure here, which influences the stress, is the one that gives the coupling back from the flow to the mechanics.
What is eta?
Eta is the which eta is the one?
In the Darcy's law, the one after rho FG grad eta.
Oh, this is just the height. So if you want to have the gravity, so you could just replace it by g, and you could forget. So this is just the difference in the depth. So this is the model equation that I'm working on. I asked for some papers from John to to look at the model equations that are being studied in the two-phase flow melt transport model, and I saw that so Bergen, after some of the simplifications, at least this is what I saw in his paper, which said constant shear viscosity, constant bulk viscosity, permeability independent of porosity, and so on. So after a bunch of assumptions, the model looks something like this. So U is the matrix velocity, P is the pressure, and you see some similar structure. And let me make it a bit more explicit. So if you see the two models, and I try to put it close enough to each other, so you see I have similar terms. So divergence of du, grad P, alpha divergence of u, and the gradient. This is gradient of lambda divergence of u, and some forcing term which let us say will not matter much. The second equation is a bit more, it seems a bit more different, because the first one is really very close. The second one is I take a time derivative of pressure and a time derivative of divergence of u, and here you have only divergence of u, and the rest of the term are similar. I mean, I changed the notation a bit just to denote that there is some force here, but I think this would be similar force as you have in because it's the gravity. So the difference now is in this term where we have one is the parabolic part here, the beta delta p, and the second is instead of divergence of u, we have a time derivative of divergence of u. So it's not too different. In fact, if we go a bit further and I discretize in time, then what I will get is I will get a linear term in pressure, and I will get a linear term in divergence of u. So if I am doing some kind of iterations, as I will show, the structure basically will exactly be something like this. So much of what I am going to see to say here would up to, this is not a serious investigation yet, this is just what I have seen, and I have tried to make a correspondence, but so far it looks reasonable. But my optimism in the past has gone wrong. So, so if I have seen these models, okay, I think this should correspond well. But this, and of course, I mean, in this melt transport, you have one more equation which I forgot, which is that your phi evolution of the phi has another equation, and this alpha, k, and I don't know, eta, probably they are all functions of this phi. But also when you solve, you usually solve this decoupled from the phi equation. So then it is not too. There is quite some correspondence that we can draw. Okay. So then I go back to the model that I was considering. And so I have two unknowns, displacement and pressure. And please interrupt me if you feel like. So what we have is a fully implicit approach where you take both U and P as unknown and you form the matrix. Of course, this kind of a step, what I'm saying here is not only for single phase, but it is also for nonlinear flow, nonlinear mechanics, and so on. And there probably this is more crucial than in the single phase. But in any case, if you have a fully implicit way of solving, so that your linear system has both U and P as unknown, then it's a very nice way to solve. It's stable, convergent. But what you have done is you have given the linear system too much responsibility, because it has now both the operators from the displacement, as well as for the flow. And because of quite some difference of orders of your parameters, these matrices can be quite ill-conditioned. At the same time, you have also very efficient solvers separately for each of them. You have developed very good preconditioners for flow or for mechanics separately. And those things you will not be able to use if you continue solving full implicit, because then you have to develop preconditioners specific to these problems. The other extreme is, of course, the explicit coupling, which of course is easy to solve, easy to implement. The only trouble is it is only conditionally stable. When I say explicit, it simply means that, you see, I have a time-dependent problem without the phi, yeah? So I have a time derivative of pressure. So what I can do is I solve my mechanics, I go to the next, I solve my flow and mechanics, I go to the next time step, I then I take the mechanics from the previous time step, and then I keep marching in time. So that's really fully decoupled. The only trouble is that if you continue like this, and if the parameters are not in the good regime, you will see that it will be unstable. So this is something that is not so difficult to see. A nice compromise between the two is the iterative coupling. In this iterative coupling, what we do is you still decouple the problem, and then you iterate between the two. So when you iterate, of course, you have to design it in a way so that it retains the stability and the convergence properties, because otherwise, I mean, the iteration, then it has no advantage. So this is the, so here it has a nice, it is decoupled, it is stable, it is convergent. The only question is, how do you design it? So that's the key question. So this is what I'm going to talk about. And there are three objectives that I'm going to follow. One is to develop multi-rate schemes to exploit the different time scales of mechanics and flow. So what happens is that the mechanics, at least in many of these geomechanics problems, mechanics response is much slow, and the flow response is much faster. So what you can do is you can take several steps of the flow and a larger step for the mechanics. So this is what I mean by multi-rate schemes here, where I can take multiple steps for the flow and a large step for the mechanics. And then the question is how to define an iterative scheme, or should we go explicit in the sense that I take Q steps of the flow, then I go to mechanics, update the mechanics, then again go to the Q steps for the flow, and this of course is going to be much cheaper because I'm taking only Q steps for the flow for each mechanics. They are still decoupled, I'm still marching in time, so there is not much, of course then there would be a trouble with the stability. So we have to find the correct then parameters or the ranges. And of course the questions are the convergence of the scheme, the stability of the explicit coupling schemes, and the computational efficiency, efficiency versus accuracy, and this kind of questions. The other kind of question is, can we localize such estimates? And when I say localize is because we have a heterogeneous media and these parameters are varying. And when we design these iterative schemes, you will see that I have to add some stabilization term, which basically when it converges, those terms do not really contribute. So it's term like one iteration minus the previous iteration. So when these iterations go to limit, this term does not contribute. And this is essential if you want to decouple the equation. This is essential because if you do not have it, you can show that you will it will be unstable. And then the question is, so this term basically depends on the BO coefficient alpha, which was in the equation, which will come again, and this lambda, which is in front of the divergence of u in the mechanics equation. So it depends on some of these parameters of the BO. Now imagine that in some places alpha is degenerating or lambda is degenerating. Then this estimate that we derive, it is something of alpha square by lambda type. So you can say I will take the maximum alpha and the minimum lambda, and that will give me the maximum. I mean, it will make it safe for the stability. But then if lambda degenerates, then basically you are adding a lot more stabilization term, which also affects the convergence rate. So then you are adding so much that basically you are slowing down the convergence everywhere. So you need to somehow localize it so that you can say that I will add alpha of this part and lambda of this part, and not the whole alpha and the whole lambda. So localization is an important, especially for the fractures where some of these quantities do degenerate. You need to have the right scaling, because otherwise you will be making it very, very slow. And then the question is, what do we get when we try to localize? So we do lose a bit, and we need some conditions, but essentially we get a much better rate. And then the third objective would be the extension of the BO model. So there has been quite some work in the direction of extending this BO model to much more complicated situations. What is presented here is the simplest that is possible. So single phase flow with linear elasticity of the mechanics, and everything is linear. Of course, but in reality we have non-linear BO models. We have something like a two-phase flow model, which is coupled to mechanics. So two-phase flow, not in this sense, but more a two-phase flow plus mechanics. So then you will have three equations. And you can consider several further extensions. So we have transport, and of course this is too much of a work. So I will only present part of this very small part that we have been touching, more or less, than something exhaustive that we have. So these are the three objectives, more or less, that we are going to pursue in this talk. So the scheme that I'm going to present, this is not the scheme that I came up with. This is a scheme which has been used for quite a while, I think at least 15-20 years, and this is called fixed stress algorithm. So what we do is, you have a flow and you have a mechanics, and now you have to iterate between the flow and mechanics. So what one does is the following. You define a quantity called mean volumetric stress, which, if you see, has a combination of both mechanics as well as the pressure. So it's a composite quantity. It is not pure mechanics or flow, but it is a composite quantity. And what we are going to do is, basically, when we solve the flow, then we use instead of just using un, basically we use sigma n. I will come to the equation, and then you will see that basically what it means is adding a term in the pressure which is of the type pi minus pi minus 1, where I is the iteration index. Yeah, because if I add L or some quantity, then basically you can see that sigma n will have divergence of un and minus alpha pn, and I will add sufficient amount so that I will get here pi plus 1 and pi, for the iteration, and then you will see that this is nothing but some kind of a stabilization term. This is key. And once you have solved this flow, then you solve the mechanics, which without any change, and then you iterate And this you do at each time step. So n is here iteration, and I did not put the time step, but it will come. Yeah. So let us see what happens in the case of multi-rate. So in the case of multi-rate, we have several flow steps for one mechanics step. So let us see the following. I have a delta t which is for flow. I will take q flow iterations for each mechanics solved. So for mechanics, I will have a q delta t step. And what I do is I solve the flow q times. I solve the mechanics. And then because I want an unconditionally stable, so I want an iterative scheme, then I have to again go back to the flow and solve it again. So it will have much more solves, yeah. And of course, if you do it only once, then that is your explicit multi-rate, in the sense that you just do flow, mechanics update, flow, mechanics update, and so on. In this case, when you are iterating, of course, you are increasing the computational cost. I will come to the numbers, how much you can save. But then we can show that it is unconditionally stable. And it will always come. Yeah, please.
The time step that you're using for the flow is a explicit time step or an implicit time step?
No, it will be implicit. So flow you solve implicitly. And so you take delta t and you solve the flow, basically whichever algorithm you want to use. I mean, we are using implicit for flow. Because we have a diffusion type term, yeah? We have a permeability type term, so, and I have a time derivative, so it would be a parabolic type problem. So I need to use an implicit method.
Does the flow depend on the state of the mechanics system?
Yes, it does.
Those internal stages?
In the internal stages, no. So in the internal stages, I just use the u that I obtained from the previous iteration.
So this whole thing is only first order in time, even after convergence?
Yes.
I mean,
The whole scheme in time will be always first order. Okay. Yeah, but I do iterate. So the system that I converge to will be a fully coupled system. Yeah, it will be a fully coupled system. But again, the coupling will be with one mechanics step with several flow steps. Yeah, so indeed. Okay. And now, so there are too many indices, but I only want to point out this term L that is being added. In this case, it looks a bit too complicated to comprehend because of too many indices. In the multi-rate case, because of you have several flow steps, then you have one which is the iteration between the flow and mechanics, and then for the mechanics you have one, and flow you have several. So then, to some extent, this is unavoidable.
you always solve flow only with an iterative method too.
Sorry? Oh, I think if we want, we can go to Newton and then to the linear solve. And then there will be two more. But I only want to point out that this L is a coefficient that we leave it undetermined at this point of time. And it is this L that we will determine by proving that the scheme converges. So the proof of this convergence of this scheme will give me which is the appropriate L. So L at this point is undetermined, but then we will get a very precise value for L in terms of the coefficient of the problem by showing that indeed this kind of scheme is convergent. So let me go further, and this is a bit of a proof, but I really do not want to go into all the details of the calculations. I only want to point out the simple algorithm. The algorithm is quite simple. One, the first step is you look at the flow equation. You use the usual estimates for the flow. So you take the test function, you try to find estimates. Then you define a composite quantity as in the single phase flow, which is again a combination of the pressure as well as the mechanics. For this composite quantity, we will prove a contraction. And this contraction would be that if you are at a step n, if you are at iteration a step n, then this delta is the one which is basically difference between n and n minus 1. And what we show is that the difference between two successive iterates is decreasing at least with a coefficient which is strictly less than 1. So basically you have a contraction. You have a quantity at n minus 1, so this is the error in one iteration, is less than equal to gamma n minus 1 minus n minus 2. And this gamma is strictly less than 1. So then you really get a Banach contraction type argument that give you that ensures convergence and so on. So this is more or less the idea. The rest is all and the step is you treat the flow, then you treat the mechanics. The mechanics is the standard, there was no change. Because of the multi-rate business, you have to, do a bit of manipulation, algebraic manipulation and so on. You have to be careful at which step you sum which step. So this is all that. And once you have done the flow and mechanics, then you combine them two, and then you get your estimate. And I only point out the following part. Okay, not yet. You have a delta sigma Vn. Remember that the sigma was a composite quantity between pressure and mechanics. And delta sigma n is basically the difference between the iteration n minus 1. So delta is this iteration. We have a lot of deltas and all the deltas. And what I want to get is on the left also I want to get a n plus 1 type term. Yeah, delta sigma n plus 1 type term. If I will have that, and if this coefficient is strictly less than 1, then I'm doing very well. So indeed, then you have to do some kind of algebra. And the final result that you get is indeed that delta sigma Vn plus 1, so n is the iteration. So this is the difference between two successive iterates. This is strictly less than delta sigma Vn by a factor which, if you see, as long as L is positive, and in fact this term is positive, then you get this is a number which is strictly less than 1. And this is exactly the number that stands in front of the time derivative of the pressure. So in this case, the time derivative of the pressure, that coefficient, I could not let it go to 0. But this is not completely true, because if you see, I have the flux which I have not used in the estimate. So what I can do is I can use this flux, get basically a coercivity in the pressure, and then I will get even better, I will get some L plus something, and then this term can also go to 0. So then again you can get it much closer to the setting of the two-phase flow, that is what you are studying. So it's not too restrictive in that sense. And so you see, and then we have a bunch of these positive terms, which you use it to prove that, because you see I have a sigma, which is the composite quantity. So if we want to prove that this whole scheme basically gives convergence to the original equation, then we have to use some of these positive quantities to get estimates. But the main point is that the iteration converges at a geometric rate. So if L is, for example, equal to this, you get more or less half. So you are decreasing every time by 1/4. And this could be quite nice because In fact, L, this term is monotonic with respect to L, so you have to choose something, and according to this algebra, you have to choose, the best is when you take alpha square by 2 lambda. So this is the one that gives you the best contraction rate. So this is a result, and we also did some numerical calculations, and we saw that we predicted a 10 minus 3, but we see that the numerical gives you much better. And this is, of course, not too unexpected, because we have this term, this term, this term, which are not being accounted for. So you only take this term by this term, and then, of course, you have much more positive terms. So it's not surprising that you get a bit better in the numerically than. So it really converges very fast. It converges in 2-3 iterations, usually. But also, I mean, it is a matter of which numbers you have chosen, which parameters you have chosen. And then the question is, can we localize these estimates? And again, I will not go much in the details, but let me just point out that I presented the fixed stress splitting, which was, if you recall, I was stabilizing the pressure term and not the mechanics term. But of course, you can do the same thing when you stabilize the mechanics and you can leave the flow. And again, you can repeat the same business. This is again not a scheme that I came up with. This is called untrend splitting. What we have done is to give a multi-rate extension of this, and we have defined a multi-rate iterative scheme. But untrend splitting as to in the mechanics equation what should be added. In the literature, what is being added is not the optimal. The analysis tells you that in fact we can take what they are adding currently, we can take half of it, and that is the at least from what we see is the optimal number. So this kind of proof that we have done also can give you an optimized algorithm, at least in the way that we have seen. So it is better, that number is better than what is reported in the literature. And one can do the same story for the untrend splitting. I will not go again in the details, except for saying that again the quantity that we want to get a contraction on is a composite quantity of mechanics as well as for the pressure. And we study the difference of two successive iterates, and on this difference we are going to get a contraction. So more or less the same story. And again we do the variational formulation. Again the steps are the same as, so this is the reason why I put it, because this really is a well-defined procedure to study this kind of problems, where you take the mechanics equation, you get the estimates for the mechanics, then you consider the flow equation separately, get the estimates, and then you combine mechanics and flow, and then you will see a bunch of free parameters, which you use then your algebraic technique in order to get again the contraction. And in this case, we get a contraction factor of L square upon lambda plus L square, and we also get a Q, which is this multi-rate factor. So Q is the number of flow steps that we take for each mechanics step, and this contraction factor, as you can see, is strictly less than 1. If you take Q large, you get smaller contraction factor, but this may be a bit deceptive in the sense that you will say, why not take Q very large? Because remember that our flow step is delta T. So if you take Q delta T, then Q delta T is also becoming very large. So you're also leading to a lot of error in the mechanics. And then the result is something similar. We have this quantity M. There is also another M, but so this should be changed. But this, so we have a delta M here, delta m there, this is n plus 1, so indeed, and this quantity is strictly less than 1, the rest are all positive, so you really see a contraction. And then you can determine all this number, L was the one that was needed for the scheme to be precise, and this is the number that you get there. Yeah, so this is the number that you need to use. For the localization, what we need is, what we have to do now, so again, repeat more or less the same procedures, so I will not go into the details, but the strategy is that you take a grid element EI, you do the contraction proof locally for each grid element EI, you will of course get the boundary terms, and then you continue, but now you cannot really multiply by the coefficients because they are all now dependent on x. So this is something that you need to worry, like how to have this procedure. But once you have continued being carefully not multiplying by the space-dependent numbers, then more or less you continue the same procedure. You sum across all grid elements, and then you will see that the boundary terms will cancel, and then you get the same version for this. So again, I will skip the proof, and then you can show that basically what you are getting is Li, which I is the grid element Ei. So now you see I have been able to localize it in the sense that I can take different L for different grids. And it's still, so now I'm losing the square here, which would have been much better, but it seems to be something that we could not avoid because of now the less optimal way of proving things, because we could not multiply by the quantities and form squares and so on. And the same thing you can do for, this is for single rate, but the same business you can do for the multi-rate, and things work out okay. So only I will just present the table that in the homogeneous poroelastic medium, it is not exactly homogeneous. We could take alpha dependent on x and lambda dependent on x, but you have to take then the maximum alpha and the minimum lambda, which of course gives you a very large L, which is very much suboptimal for the other part of the domain. So I mean, it is in this sense that that you cannot, I mean, the heterogeneities will lead to a much more cost. And in this case, the parameters can be heterogeneous, and the contraction coefficients, of course, we are losing a bit, and we get this was without any condition on Q. For the iterative scheme, we could get convergence, but here we do see that we need a limit on the Q for the localized case.
How big is that Q?
So Q, we are taking, for example, 2, 4, 8, but this is something you can choose.
Well, no, you can only choose it as big as that bound. But how big
Yes,
is
yes,
that?
yes. In this,
I don't have any intuition for how big that bound
right,
is.
right. So in this case, for example, this, I mean, of course, this depends on the numbers, yeah. But this is like the compressibilities, yeah. And the compressibilities and lambdas, they are not very different scales. So you can have lambdas, for example, of, so this could give you, for example, I don't know, depending on which fluid you are dealing with, it could give you 10, 20 or something like that. But it could also be very restrictive.
So if you take a fairly large Q, then your contraction rate will be very slow, right?
No. On the other hand, if I take, but this is because the way I have formulated, yeah, my flow delta T is fixed, and Q delta T is the mechanics time step.
Yeah.
So I will also have to take very large mechanics time step. But here I see that if I take large Q, this actually helps me in my contraction.
So if you keep the flow time step fixed,
Yes.
and you take a large Q, it means that the mechanics time step is very large.
Yes.
And you're saying that converges fast?
Yes.
Until what happens when you exceed this bound on Q?
Then
It doesn't converge at all?
I do not know. We haven't checked what happens. factors, but we are not able to have the contraction.
But you never ran with a large Q and saw that it converges slowly?
No, we have not run with very large Q and then seen that what happens. In fact, we haven't done simulations with this heterogeneous case. I mean,
I'm interested in the
yeah.
heterogeneous case.
Yeah. So I want to run with different lambdas and what.
So it just works great until it doesn't work at all?
No, I haven't. I do not know with what happens when I have lambda and alpha varying. I do not have numerical simulations. This is something we have tried to.
Okay.
So you've just done the column on the left, the homogeneous.
Yes. Or in the case when alpha stays away from alpha 0, lambda, I take lambda min and then so. But this is the more localized case where for each grid element I can choose this and then I can see what happens. So this is something we are still dealing with. What we actually, the motivation was because people were dealing with phase field type models where these alphas and lambdas, they degenerate because you have the fractures and there this coefficient go down to 0. And there the question was, how should I choose my L, because there I really need, because if I really follow that, then I am doing a very bad job for the rest of the domain. And because you see in the kind of simulations we ran, it was converging very fast. It was like at the rate of 10⁻⁴ or so. So this was like very, very fast. So we didn't really need much number of iterations. So there we needed this, yeah.
So the estimate, I suppose, comes from the stability type estimate.
Yes, it is.
And so but then I'm confused. So
Yes.
you take sort of a uniform bound over piecewise constant parts.
Yeah.
So, I mean, then you might argue, I just do a domain decomposition, that all these domains step with a different rate,
Yes.
like an implicit, explicit scheme. And so this bound really doesn't play a big role in that case. I'm confused. What you're really trying to do is that right lower box. Other than just taking
Yes,
a
yes.
uniform bound over the constant, over
Yes.
all the constant pieces, but that is not very sharp. I mean, it's an extremely,
But this is
extremely
the
conservative estimate.
yeah. So this is the whole point that so the estimate that I am getting is so if I take a uniform, so the number I am getting is alpha squared by lambda.
Right.
Yeah.
Yeah.
Now alpha is in each grid value different.
Yeah.
So I have to take the maximum of alpha and the minimum of lambda in order to be safe.
Yeah, but that is an
Yeah.
extremely,
But this is-
extremely conservative.
But this is
barely a real
yeah, this
estimate.
is really bad. Yeah, in the sense that if in some places alpha is very small or very large or lambda is very small, then I'm really destroying for the whole domain.
Yeah.
So then the idea was, can we have the same kind of contraction result when we take alpha locally, lambda locally,
Right.
and this makes sense because in the matrix
Precisely.
I should be able to add
You can do a decomposition. of
precisely. So this
a
is
sure complement argument and
But this is something similar. I mean, what this whole thing is doing, this fixed stress and all this, is taking the matrix and adding something on the diagonal. This is all it does. It does not do much more than that. It just adds something, some term on the diagonal. Now, the only thing that is being said here is, this diagonal, you do not need to add the same term, but you can add different terms on each diagonal, which, of course, I think any practical person would anyhow think of doing it. But I mean, if lambda was not varying or alpha was not varying, this was no problem. But in the case where fractures and all there, it is much more critical too. So in terms of computational savings, what we have is, so if we do this iterative multirate, then we see that of course the number of mechanics solves really decreases quite a bit, which of course is not surprising because now we are solving mechanics very coarsely. So of course there is a nice decline in the number of mechanics. So this is unsurprising. However, in the CPU time there is a reduction of much less. Yeah? So it is, I mean, it is not too bad. It's like 30% for Q8 and Q4 it is 27.2 and Q2 it is 18%. And this is the reason why it is happening is that you take mechanics, okay, you take course step, but then when you take, you have to take more flow steps in order to have the convergence. So then the number of flow steps is not always working that way. So in the net, you are gaining less. So the point here is that you gain much more in this multi-rate kind of business if your mechanics solve is much more expensive compared to the flow. If the expenses are comparable, you get nothing. But if the mechanics solve is much more expensive than the flow, then of course it makes sense to do as little mechanics as you can and do more of flow, because the flow is cheap. And also in cases where you have multi-phase flow, then you have a restriction on the time step. So you cannot really take large time steps for the flow. So in that case, also it can be useful. So this is the message that I want to give. And then the similar things for other problem. Of course, the easiest is to do the explicit multi-rate, where you only keep marching in time and you never go back and solve the flow again. So you, for each, you do the mechanics update after each Q flow steps. And in this case, of course, there is no question of contraction, but the question is then the stability, right? Because I mean, you need to have the stability. And what we get is that the Q, which is the number of flow steps, now should be in satisfying this bound if it wants to be stable. So what is known is when Q is 1, then we need that this compressibility should be larger than some number if you want to have a stability. So this is essential. And now what it is saying is that you need, how to say, if you want to take Q flow steps, then you need to satisfy this kind of situation. So then the compressibility has to be even larger. Yeah, and actually this is something that is very much used in practice. So people are not really going back and iterating and so on. They really just solve the flow, then update mechanics once in a while. And this is a useful estimate to know as to when this will be stable and when it will not be stable, or what kind of how many flow steps I can take if I want to continue this business. And so of course between the iterative and the explicit, no surprises that if you do iterative single rate, then you are taking much more step, and when you are doing it single rate explicit, if you do implicit, then you are taking like 40, 45, and if you do explicit, then you are taking like 10, 11, 12, whatever. So you see a lot more saving in time. And similarly for all this. So this upper part is the iterative one, lower part is the explicit one. So you see that the explicit, of course, has a lot of CPU time saving. Of course, this is a balance because the stability in this case is not assured. So it is possible that for some parameters you will, you will not converge, but at least in this case you will converge, but then you pay by doing more iterations. And similarly for the number of flow iterations you can compute. So I mean, again, no surprises that the explicit will beat in terms of number of flow iterations. Then the question is how what should be the strategy for the maximum computational efficiency? And also an important question, at least we think, is to try to have some a posteriori error estimates as to when we should stop with this iteration business. And what we are doing is we are combining these contraction estimates that we have with, for each equation, there can be some measurements that will give you the error that is happening based on the numerical solution that you have obtained. And then you can combine these two to get some kind of a posteriori error estimators. We are doing this with people from St. Petersburg and Universitetet, with Sergei Repin and Jan and Svetlana. And now to some of the extensions. So what we are trying to do is, we have a BO model, and then we are trying to do is to add some more physics. So in this case, what I'm considering is the fracture. And now the fracture is a surface which is embedded in the domain. So you have one porous media domain in which there is a surface which we call fracture. On this surface, we have a differential equation of same type as Darcy. So you have a surface which has a Darcy law in it, and then it is coupled to the domain, to the matrix. So this is a PD on a surface coupled to the BO equations in the domain. The coupling is via the width. So this width of the fracture, basically, which comes by solving the mechanics equation. And then the leakage term, which basically couples the flow term. And also this K, this permeability in the fracture, is a function of width. So there is quite some strong coupling for this problem. And for the mechanics equation, the reservoir pressure P enters as right hand side, and this fracture pressure enters as boundary condition. So you have quite some coupling between the two. And what we have been able to do is to do an existence of a discrete solution using mixed method, and we have proved the stability, the error estimates, and it's a bit technical work because of the presence of this width in the permeability, and the width can go to 0, so it degenerates, and then one has to consider weighted Sobral spaces and so on. And what we have done is again extend the fixed step type algorithm for the case when you have one more equation. So, and this is something that we can also use the same kind of strategy if we have some more equations which is coupled to this two-phase flow model or this BO type model. So the same kind of ideas we can follow. In this case, again, what I have to do is to do a similar term as I do for the domain. I define a sigma, which is the composite of pressure and U, and I define a similar quantity for the fracture, which is again a composite of fracture pressure and the width. And then the rest of the, with some undetermined coefficients, which again will be determined by the proof. We get the same kind of result where the two consecutive iterations, both in the matrix case, this matrix composite quantity and the fracture composite quantity is declining at a rate which is strictly less than 1, both sides, and you can prove then that the converse solution also solves the weak. I have to say that this proof is done when I have assumed permeability in the fracture to be constant. So this is an important simplification that I have made. I have not been able to obtain any results when this K is a function of width, because then you make a difference of iteration, then K becomes a function of this difference of the iterates, and then you have to control these terms, which were not so easy, because then W is on a lower surface, U is in the domain, so you really need to have extra regularity and so on in order to control them. So, but the procedure is similar to what we have done for the other case that I presented. So again, we solve the flow, we estimate the flow, we estimate the mechanics, we put it together, we do the algebra, and so on. And again, of course, the question is what kind of shapes of the fracture are the worst ones. So this is something important, because in the proof we see that so this proof only works if you have put some conditions on the fracture on the how much the fracture width can change as I change the iteration. So there is some condition on the parameters which allows us to make this proof. And from studying that, I think we will be able to obtain some idea about which shape of the fracture would be the worst one. And just to finish the last slide, the nonlinear extensions that we are trying to do is to consider sigma as some nonlinear function of divergence of u and this symmetrized gradient of u. And then again, so this case I still keep this part linear, yeah, and then I have this divergence. And then the flow we can consider instead of taking p, but we can take some function of pressure, and then we can do. So we have been able to do it when f is, for example, linear in this. We can also take nonlinear in this, but then we have to put some structure on the nonlinearity of divergence of u, and this some of this we are able to do, but of course this is much more difficult if we go to stronger coupling. So for example, this is single phase, but if we go to two phase, then we have saturation that comes up. The saturation can degenerate, and then this saturation, this alpha becomes a function of saturation. I mean, so the function that comes up here is a function of saturation and pressure, and then the coupling becomes much more difficult to do. And those things we are still struggling to do. So let me just acknowledge support from affiliates program from Center for Subsurface Modeling at Austin, a Statoil Academia grant for travel, Ivan Yotov and Paulo Zunino. We had discussions on the multi-rate scheme, and I should thank some more who have sponsored my ticket here. Departmental funding and so on. So that concludes my talk, and I'm very much willing to take questions. Thank you.
Thank you very much, Kundan. Questions?
Yeah.
I think this is a clarification, but what convergence criteria do you use on the outer iteration at each time step?
Oh, you just, I mean, basically, at each time step, we have an iteration happening, yeah? So we just use some kind of, so I mean, there are different ones, yeah? So but essentially we use the difference between one iterate minus the previous iterate. And then.
So how do you know if it's converged or just stagnated?
This is very true, that in the, I mean, of course we have a proof that, that tells us that it has to converge.
Does it tell you how fast it
Yes,
converges?
yes, because of the contraction rate. So if you see, I mean, this tells us exactly, for example, let us take the first one. So for example, if I choose this L, we get exactly this rate at which it will converge.
What does that amount to in practice?
In practice, so for example, this could be 1/4. So I said, okay, if I take L, which is something similar to this compressibility, which is possible in practice, not too far, then it will give you like 1/4. So 0.025, or if you choose something smaller than further small. So for example, one numbers that we took, we had like 10⁻³ for this number, and what we saw numerically was that it was of the order of 10⁻⁴, because the estimate that we make, it also has some more positive terms on the left, and that we did not take into account. So this we only considered like the two iterates of sigma, and that was decreasing very fast. So yes, we do have, but this is of course an upper bound. In practice, it can converge fast.
Any more questions? In which case, can we just thank Kundan once again? Thank you very much.